Welcome everyone to today's webinar. My name is Arya Hakimian, an application scientist here at C-Therm. And today we're looking at material testing for the development and design in both wearables and humanoid robotics. I'll be joined throughout today's session by two of my colleagues, Alex Mann, as well as Arya Shadowstembik. So we'll be talking about various areas of application from both thermal and mechanical testing perspectives as we go through today's content.
So this is an application for service robotics and prosthetics. This was a Nitinol skeletal framework hand designed by Lee et al. So what this does is it mimics the full carpal and metacarpal anatomy of the human hand. So it just helps with, grasping objects and creating a robot with a hand that can do what the human hands do. So it actually employs the use of nitinol, which is a nickel titanium alloy that exhibits shape memory and superelasticity. So nitinol is actually fairly elastic for an alloy. In its superelastic phase, it has a deformation that can be anywhere from 8 to 10% before it can snap back to its normal rest position. So what they found was using this nitinol for the framework, they could get a palm deformation of around 28%, which is the exact amount that a normal human would have. And although the palm deformation was matched, actually the payload capacity of this hand was twice that of human capacity. So this is actually a DSC view of a run of nitinol. So we can see during a heating and a cooling cycle, there are 6 points that have been labeled. When working with nitinol, it is important to know all of these points. So we have the start, the peak, and the finish of the martensite and the austenite phase transitions. So in the austenite phase, this is where the alloy exhibits its superelastic properties. So this is on the hot side or the higher temperature, also known as the parent phase. So in this phase, this is where you can deform it up to 8 to 10%, and it'll immediately snap back when the force is released. Then in the daughter phase or the martensite phase, this is where we get the shape memory effect. So we set the neutral phase in the austenite, and then we cool it down to the martensite. Then when it's in the martensite, it's actually very flexible and malleable. We can bend it to any shape we like. And then when we heat it back up to the austenite, it'll snap back to our predetermined neutral phase. And this is what's known as the phase memory effect.
Simplifying thermal conductivity.